Hello everyone, my name is Maria and I'm the problem captain for problem 3. And in this video we're gonna explore the first solution from the problem selection committee. Okay, so let's just quickly recap what problem 3 says. So we have a convex hexagon and the angles at A, C and E are equal, and we denote the value of the angle by alpha, and the angle at B, D and F are also equal, and we denote that angle by beta. It's also specified that the bisectors of the angles A, C, and E, which we denote by small letters corresponding to the angles, same for the others, B, D, and F, meet at the same point, which we denote by M. And then we are asked to prove that the other bisectors, B, D, and F, meet at the same point. Okay, just before we start the proof, let me just quickly recap for you what a directed angle means, because we're going to work with directed angles. And the reason is we want to avoid special cases such as when the intersection points are inside or outside the hexagon. And those directed angles cover those cases for us. Okay, so a directed angle between lines X and Y, which we'll denote like that, will be the angle mod 180 degrees of clockwise rotation that takes line X to line Y. So just a small example. If this is X and this is Y, we're looking for a rotation counterclockwise that will take X to Y. So it would be like that, and therefore the directed angle would be this. Okay, so we're going to work with directed angles, and this is going to be our rotation. The first observation that we can make is since the sum of the angles in a complex hexagon is 120 degrees, then we get that alpha plus beta is 240 degrees by just a simple computation. Okay, so in particular, if we look, let's say, at these two bisectors A and B, the angles in here will add up to 120, so half of this one. Therefore, the angle between themselves is going to be 60 degrees. So we're going to have that the angles, now the directed angles between B and A, the directed angles between C and B, and so on, equals directed angle between A and F, and equals 60 degrees. Okay, but we are told that something happens with the three bisectors A, C, and E. So it's natural to look at the directed angle between A and C. That angle will be the sum of the directed angles between A and B plus the sum of the directed angle between B and C, which with this assumption over here is going to give us 60 degrees. Remember, these are directed angles. Okay, so if we rewrite this in terms of our points of the figure, this is the angle between MA and MC. The next thing that we're going to do is we're going to extend the sides AB, CD and EF. And they meet at X, Y, and Z. And we can make the same for the other side. BC, ED, meet at T. These two meet at Q. And these two would meet at R. Right. Now, the first observation that we can make is because the sum of these two angles is 240 degrees, the sum of these two angles is going to be 120, therefore, these angle is going to be 60 degrees, and the same can be said about all of them. So, another observation is that triangles X, Y, Z, and PQR are equilateral. Moreover, from here, let's use what we discovered here, that the angle between MA and MC is the angle between RA and RC. And is the angle between XA and XC. From the fact that they are equilateral and they are equal to 60 degrees. So from here, we immediately deduce that the points R, A, and C, X are concyclic. So R, A, and C, X are concyclic. But M is not any point. M actually lies on the bisector of the angle RAX, the outer bisector. So M is on the bisector of the angle RAX. And together with the fact that these points are concyclic, this gives us that MR equals to MX. But also from the fact that these are concyclic, the angle between MR and MX is the angle between CR and CX. And if we look at our picture, that angle is exactly alpha. Okay, so now we have that R and X are the same distance away from M, and the angle between them, the directed angle, is equal to alpha. But by the same argument, we will find that P and Y, Q and Z will obey the same conditions at the points as the points R and X obey. So that will tell us that in fact we have a rotation centered at M with a directed angle of alpha that will take one triangle to the other triangle. So this will take R to X, P to Y, and Q to Z. But this also means, because if the triangles are just rotated, it means that they are actually congruent, not only equilateral. So this implies that triangle x, y, z is congruent to the triangle QR. So in particular, there exists a rotation that takes x to P, y to Q, z to R, with center N. Okay, so we have another rotation with these mappings, defined by these mappings, and it has center N. Let's somehow find it on the picture. This is center N. Now our goal is to prove that actually N is the intersection point of the other three bisectors. Well, let's start with the fact that it's the center of this rotation. Okay, and then we look at the triangles N, X, Z, and N, P, R. Because it's a rotation, these triangles are congruent. So triangle NXZ is congruent to triangle NPR. In particular, NP equals NX. Okay, but also because they are congruent, these two angles are the same, and we can deduce that BX PN is cyclic. So we have this quadrilateral here. Let's write that down. BX PN. Okay, so BXPN is cyclic, and we also know that NX equals NP at distances. Therefore, exactly as before, it will follow that N is on the bisector of angle. Now it's B. Note, it has to be actually on the inner bisector because this rotation is a clockwise rotation. So note, N is on the inner bisector. Okay. So therefore, analogously, N is on the other bisectors as well, so F and D. And the problem is solved, therefore N is the intersection point of the other three bisectors.